Number 25 says, a 0.25 kilogram ball is attached to the end of a string. It is swung in a vertical circle of radius 0.6 meters. At the top of the circle, its velocity is 3 meters per second. Part A. Draw a free body diagram for the ball when it is at the top of the circle. Next to that diagram, indicate the direction of its acceleration. So when drawing a free body diagram, we usually just draw a dot to symbolize the object. Now in this case, it's at the top of a circle, so it might help us if we understand that there is a circle surrounding it. So with our ball at the top of the circle, we know that we always have our force of gravity pulling downwards. When we're talking about circular motion, and since this is attached to a string, we're also going to have a second force going towards the center of the circle, and that is going to be our force of tension. Whenever we have something attached to a string, remember that is the tension force that is on the object. They also ask us to indicate the direction of the acceleration, and when we're talking about circular motion, our acceleration always goes towards the center of the circle. So since our object is at the top of the circle, our acceleration will be going in the downward direction. In part B, they ask us to use this free body diagram to set up an equation to determine the tension in the string. So for part B, we're going to be talking about our net force, and we know that our net force equals mv squared over r when we're talking about circular motion. So as far as our net force is concerned, we have our force of tension and our force of gravity. They're both going in the same direction, so they'll be added together, and that will be set equal to mv squared over r. They ask us to solve for tension, which means we'll have to subtract our gravity from both sides. So it will cancel on the left, and we'll be left with a force of tension equaling mv squared divided by r minus mg. For part C, they want you to solve the equation for the tension in a string. So using the equation, we can plug in our numbers. So we have our mass of 0.25 kilograms, our velocity of 3 meters per second, which gets squared, divided by a radius of 0.6 meters, minus our 0.25 kilograms times 9.8 meters per second squared. When we calculate this, we can simplify it down to 3.75 newtons minus 2.45 newtons, and we ultimately get an answer of our force of tension equaling 1.3 newtons. Moving on to number 26. Again, a 0.25 kilogram ball is attached to the end of a string. It is swung in a vertical circle of radius 0.6 meters at the bottom of a circle whose velocity is 3 meters per second. So we have a very similar problem to number 25. However, instead of being at the top of the circle, it is now at the bottom of the circle. So for part A, if we imagine our circle again, our ball now is at the bottom. So in drawing our free body diagram at the bottom of the circle, our gravity is now in the downward direction away from the circle. However, our force of tension is still towards the center. And our acceleration is also going to be towards the center of the circle. So that completes our free body diagram for part A. For part B, again, they want us to set up the equation for tension. So again, we start off with our net force equaling mv squared over r. In this case, we have our force of tension subtract our force of gravity, and that will equal our mv squared over r. In our previous equation, we were adding our force of tension and our force of gravity because they were going in the same direction. In this equation, they're in opposite directions, so they'll be subtracted. But we need to solve for force of tension and get that alone. So we'll add mg to both sides, and we'll end up with the force of tension equaling mv squared over r plus mg. Then for part C, again they ask us to plug in and solve for tension. So again we plug in all of our numbers. We have our 0.25 kilograms, our 3 meters per second, that gets squared, divided by our 0.6 meters, and that again will get added to our 0.25 kilograms divided by our 9.8 meters per second squared. Again, we can simplify down to 3.75 newtons, this time plus 2.45 newtons. So it's the same number value. However, last time it was subtracted, this time it's added. So this time we end up with a force of tension equaling 6.2 newtons. And so that is our answer for part C.